There is another test besides the first derivative test for determining whether or not various critical points correspond to local minima and local maxima. And that's the second derivative test. And as you may expect, it involves a second derivative. Let's bring up the test in words, and then we'll do the corresponding illustrations, which I think will make a little bit more sense. This can get a little wordy, but when you see it in pictures, it's really pretty clear. So we start with our conditions. Suppose f double prime is continuous on an open interval containing the point C, with f prime of C equals 0. Okay, so this works for a certain kind of critical point where the derivative is 0. So we know something might be up there. We're thinking it might be a maximum or minimum. Maybe it's not, though. So let's see what we have now. If the second derivative of C is greater than 0, then f has a local minimum at C. So what does that mean? Remember that if the second derivative is positive, that tells us that the thing is concave up, right? Well, if it's concave up, then it must have a minimum. So it's a little bit counterintuitive because we usually think as positive must correspond with maximum somehow. But in this case, the positive version for concave up means that our point of interest is a local minimum. Okay, the second part of this says that if f double prime of C is less than 0, then f has a local maximum at C. Okay, well, let's think this through. If the second derivative is less than 0, then it's concave down, right? But if it's concave down, then the thing at the top of it must be a maximum. Okay, so we have some curve here, and we know something's going on at C. And if it's concave down, then right at that point C, right, we're concave down, so then that must be a local maximum. But of course, it's not a perfect test. For the last part we have, if f double prime of C equals 0, then the test is inconclusive. F may have a local maximum, a local minimum, or neither at C. So sometimes you have to give it a little bit more thought, and that's okay. So when you imprint the second derivative test into your brain, really just, at least the way I think of it, is just remembering a couple of the pictures. It really tells the whole story, right? All these words, it's just telling us something very intuitive. Concave up, right? It must be a local minimum. Concave down, it must be a local maximum. That's really the takeaway here. Let's try an example. For f of x equals e to the x times the quantity x minus 7, find the critical points and use the second derivative test to determine, if possible, if they correspond to local maxima or local minima. Okay, let's do it. First we find the critical points, and remember those are where the derivative either equals 0 or does not exist. So let's take the derivative and see what happens. We have f prime of x. Alright, so we have a product here, e to the x times x minus 7. So we'll use the product rule, a prime b plus b prime a. So a prime b is e to the x, x minus 7, plus b prime a. Well, the derivative of x minus 7 is 1, times a is e to the x. Okay, and this is what we want to look at. Where is it equal to 0? Well, how in the world do we solve that? What if we factor out an e to the x out to the front? E to the x, this then becomes x minus 7 plus 1 equals 0, and e to the x, x minus 6 equals 0. Okay, so first off, note that there's nowhere that this is undefined. So really we're only looking for points where it equals 0. There's no way for e to the x to be equal to 0. Right, so we'd set each one of these equal to 0. E to the x equals 0? No. Well, why not? Well, there's a few reasons why. I recommend carrying around a graph of e to the x, which looks something like this. And note that it asymptotically approaches 0, but it never equals 0. And by carry around, I mean mentally carry around. Right, it answers a lot of questions about exponential. This same graph works for any exponential function with a base greater than 1. And it answers a lot of questions about the function in one simple picture. Okay, so there's no way for that to be equal to 0. However, we can get clearly x minus 6 equals 0. X minus 6 equals 0, which gives us x equals 6. So there's our critical point. Okay, so we found our critical point. Now to use a second derivative test, we take the second derivative and plug in that point to see if our second derivative is positive or negative at that point. Okay, so let's take the second derivative, f double prime of x, and recall that the first derivative that we're working off of is this bit here, e to the x times x minus 6. So then the second derivative is the derivative of that, so we again do the product rule, a prime b plus b prime a, e to the x minus 6 is a prime b, and then plus b prime a. Well, the derivative of x minus 6 is 1, again times e to the x equals 0. Actually, we don't even need equal 0 here. I get so used to setting things equal to 0. It's a dangerous habit to get into. We're just trying to simplify this. So let's see. Let's factor out e to the x. And we get x minus 6 plus 1. So finally, e to the x times x minus 5. So we are now finally ready to use our second derivative test. And we just plug in f double prime at 6 to see, all right, where did that 6 come from? That's our critical point. To see if it's positive or negative, well, e to the 6th times, and we don't really need to know what it is, we just need to know the sign of it, 6 minus 5, I'm thinking that's positive. Positive means it's concave up. So what does that mean? And again, I recommend just kind of running through a picture. If it's concave up, that means this point must be a minimum. That's what the second derivative test tells us. So we conclude that there is a local minimum at x equals 6.